We are stardust contemplating the stars. The cosmos is within us, as Carl Sagan once said. We are made of star stuff, but what does that truly mean for the nature of your own reality? This is a deep dive into the unscripted universe, a place where the fundamental rules are not a fixed script, but a living tapestry of profound mysteries. By the end of this journey, you will see the cosmos and your place within it in a completely new light. We will confront the invisible matter holding galaxies together and ask if your own consciousness might shape the quantum world. What single mystery of existence keeps you up at night, staring at the stars? The stars in a galaxy whirl around its center at such tremendous speeds that they should be flung into the void. This was the stark reality Vera Rubin observed through her telescope, a cosmic contradiction that could not be explained by the gravity of the stars we see. An immense, unseen presence was holding the universe together. We call this ghostly substance dark matter. It is the universe's greatest sleight of hand, a form of matter that makes up roughly 27% of the cosmos, yet it does not emit, absorb, or reflect any light. It is utterly invisible to our eyes and every telescope we have ever built. We only know it is there because its immense gravitational pull dictates the motion of galaxies. As physicist Lisa Randall noted, dark matter is the most mundane of the exotic substances we have imagined, yet it remains stubbornly out of reach. Its nature is one of physics' most profound puzzles. What could it possibly be made of? The leading candidates have names that sound like science fiction. Weakly interacting massive particles, or WIMP, are hypothetical heavy particles that barely interact with normal matter. Then there are actions, theoretical particles so incredibly light and numerous they could flow through the universe like an invisible sea. Scientists are hunting for these phantoms in two ways. They are trying to create them in powerful atom smashers like the Large Hadron Collider, and they are building exquisitely sensitive detectors deep underground, waiting for the rare, faint bump of a dark matter particle passing through. So much of our reality is governed by something we cannot see or touch. If most of the matter in the universe is invisible, what does that say about the completeness of our own senses? This invisible scaffold holding the cosmic architecture together forces us to ask what other fundamental forces are at play, leading us to the even more mysterious agent of cosmic expansion, dark energy. If most of the matter in the universe is invisible, its dominant energy is even more baffling. The cosmos is not merely expanding, it is accelerating, racing apart at a pace that grows faster with every passing moment. Think of throwing a ball into the sky, expecting it to slow and fall back to Earth, only to watch it fly upward forever, faster and faster into the void. This is precisely what two teams of astronomers discovered in 1998, a revelation that shattered our most fundamental expectations. The universe is being pushed apart by a mysterious repulsive force we call dark energy. Nobel laureate Adam Rees described the shock of this discovery, saying it was a complete surprise, like finding a new law of physics. This dark energy now appears to be the universe's primary component, making up a staggering 68% of all the energy density in the cosmos. What could possibly possess such power to stretch the fabric of space itself against the immense pull of gravity? The leading explanation reaches back to an idea from Einstein himself, the cosmological constant. This proposes that empty space is not truly empty, but seethes with a latent energy that exerts a negative pressure, pushing the universe apart. Another theory suggests a dynamic force field known as quintessence, a kind of fifth fundamental element that changes over time. The evidence for this accelerating reality is etched into the light of distant stellar explosions, supernovae that serve as cosmic mile markers, revealing the expansion history of the universe. It is also imprinted on the afterglow of the Big Bang, the cosmic microwave background, a baby picture of the universe that confirms the amount and influence of dark energy. This relentless push forces a profound question upon us. What is the ultimate fate of everything in a universe that expands without end? Galaxies will be pulled ever further apart, their light fading from view. Stars will burn out, and matter itself may ultimately be torn asunder in a final, cold, and lonely epoch known as the Big Rip. This accelerating endgame is inextricably linked to the very nature of time and a fundamental cosmic rule known as entropy, the slow and inevitable slide of all things from order into disorder. A broken egg never reassembles itself. You never see smoke retreating into a chimney, coalescing back into a log. Our daily lives are filled with these irreversible moments, a constant reminder that time has a direction, an arrow flying forward. This one-way flow is perhaps the most fundamental rule of our existence, governing everything from memory to aging, yet its origin is one of physics' deepest puzzles. The underlying laws, like those for gravity or electromagnetism, do not actually care which way time flows. They would work just as well in reverse, so why does our reality only move forward? The answer appears to lie in a concept called entropy, often described as the measure of disorder in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Things move from order to disorder, from a concentrated egg to a messy puddle, from a hot cup of coffee to a cool one. This inevitable slide gives time its arrow. As physicist Sean Carroll explains, the arrow of time is an emergent property, not a fundamental feature of the universe. It emerges from the specific conditions of our cosmic past. The universe began in a state of incredibly low entropy, a highly ordered and dense state just after the Big Bang. Since then, it has been evolving toward higher and higher states of disorder, and we are carried along on that one-way tide. This explains why we remember the past but not the future. Our memories are formed by irreversible processes, like brain cells changing state, processes that increase the overall entropy of the universe. It underpins causality itself, the idea that a cause must always come before its effect. This relentless march toward disorder also points to a sobering ultimate fate for the cosmos, a state known as heat death. In this distant era, the universe will reach maximum entropy. Energy will be evenly spread throughout an ever-expanding void, with no more temperature differences to drive stars, life, or thought. It is the final, universal state of equilibrium, a quiet and eternal stillness. This bizarre beginning in low entropy even leads to a strange philosophical puzzle known as the Boltzmann brain. If the universe is generally random and disordered, it is statistically more likely for a single, self-aware brain to spontaneously form from a random fluctuation than for an entire, ordered universe like ours to exist. So why are we part of a vast, structured cosmos, and not just lone, disembodied consciousnesses flickering in the void? The puzzle highlights how special our initial conditions truly were. If time's arrow is not a fundamental rule but a consequence of our universe's starting state, could a different cosmos experience time flowing backward? The question is not just science fiction. It forces us to confront the nature of our own perception and the very fabric of causality. And this inquiry into the flow of time inevitably draws us into the quantum realm, where the rules of reality become even more fluid and strange. A cat sits in a sealed box. It is, according to the rules of quantum mechanics, both alive and dead until someone looks inside. This was the provocative thought experiment devised by physicist Erwin Schrödinger to highlight the sheer absurdity of the quantum world when applied to our everyday reality. It forces us to confront a concept called superposition, where particles like electrons do not have a single, definite state. An electron is not simply here or there. It exists in a blur of all possible locations and states simultaneously, a ghostly probability cloud until the moment it is measured. Only then does it snap into a single, definite reality. This dual nature extends to light itself, which behaves as both a wave and a particle. A beam of light will create an interference pattern like a wave, but when you try to catch it in the act, it arrives as a discrete particle, a photon. As the pioneering physicist Niels Bohr famously stated, anyone who is not shocked by quantum theory has not understood it. The most stunning demonstration of this is the double-slit experiment. When particles like electrons are fired one by one at a barrier with two slits, they do not go through one slit or the other. Each individual particle behaves as if it passes through both slits at once, like a wave, and interferes with itself to create a wave-like pattern on the detector screen. The truly mind-bending part is what happens when you place a measuring device to observe which slit the electron goes through. The moment you observe it, the wave-like behavior vanishes. The electron acts like a single particle going through one slit or the other, and the interference pattern disappears. It is as if the particle knows it is being watched. This is the collapse of the wave function, the transition from a realm of shimmering possibilities into a single, solid fact. This act of observation forces a profound question upon us. If a particle does not have definite properties until it is measured, what constitutes a measurement? Does it require a conscious observer? Does reality itself depend on a mind to bring it into focus? Physicists have proposed wildly different interpretations to make sense of this. The Copenhagen interpretation suggests that the wave function collapse is a fundamental, random process, and it is meaningless to talk about a particle's reality before measurement. The many worlds interpretation offers an even more staggering vision, proposing that the wave function never collapses. Instead, every possible outcome of a quantum event actually occurs, spawning an infinite branching of parallel universes. In one reality, Schrödinger's cat is alive. In another, it is dead. Both are equally real. If the fundamental building blocks of the universe are this fluid, this dependent on interaction, what does that imply about the nature of our own conscious experience? This blurring of objective and subjective realities leads us directly to one of the most intimate and perplexing mysteries of all, the hard problem of consciousness itself. Look at a simple red apple. Your eyes capture light of a specific wavelength, your optic nerve fires, and electrical signals cascade through your brain. Science can map this entire objective process. Yet, this mechanical description entirely misses the most important part, the vivid, private, inner experience of redness itself. How do those firing neurons create the subjective feeling of red, the warmth of the sun, or the ache of sadness? This is the hard problem of consciousness. Philosopher David Chalmers coined this term to separate the easy problems, like how the brain focuses attention or processes information, from the truly hard one, why and how any of this physical activity gives rise to subjective experience at all. Why is there something that it feels like to be you? As Thomas Nagel famously argued, an organism has conscious mental states if and only if there is something that it is like to be that organism. A bat likely has a rich inner world built from echolocation, a world we can study but never truly know from the inside. This is the explanatory gap. We can take a brain scan and see every synapse fire, but we cannot see the pain, the joy, or the color blue that person is experiencing. These raw fields, these qualia, remain locked within the private theater of the mind. If the brain is just a complex computer made of atoms, why does it not simply process information in the dark without any inner light? Some theories propose a radical answer, that consciousness is not a product of complex computation but a fundamental feature of the cosmos, as basic as space and time. This view, called Panpsychism, suggests that some form of primitive consciousness or proto-consciousness exists in all matter. In this view, an electron might possess a tiny spark of subjective experience. The consciousness of a human being would then be a highly integrated and complex form of this universal property. Other scientists pursue a more quantitative path. Integrated information theory, for instance, attempts to measure consciousness. It proposes that any system that can integrate information in a specific, unified way has some degree of conscious experience. The theory assigns a number, a value called phi, which represents the system's capacity for consciousness. Under this framework, the human brain has a very high phi, while a simple light switch has almost none. This leads to a staggering reflection. If consciousness is not merely manufactured by the brain, but is instead a fundamental property of reality itself, what does that say about the nature of the universe we inhabit? Are we living inside a cosmos that is, in some deep and mysterious way, awake? This idea of a conscious universe creates a compelling bridge back to the quantum world, where the act of observation seems to shape reality itself, blurring the line between the inner mind and the outer cosmos. The idea that your own mind might be the final piece of the quantum puzzle is both thrilling and unsettling. This is the radical proposition of quantum consciousness, a theory suggesting that subjective awareness is not just a passive observer but an active participant in shaping reality. It takes the observer effect to its ultimate conclusion. When a particle exists in a blur of possibilities, what force finally pins it down to one concrete fact? The von Neumann-Wigner interpretation offers a staggering answer: consciousness itself. It proposes that the wave function collapses not because of any physical measuring device, but only when the information enters the conscious awareness of an observer. In this view, your mind is the ultimate architect, transforming a sea of quantum potential into the solid world you experience. The physicist John Wheeler captured this profound participatory role with his famous statement, "We are participants in bringing into being not only the near and here but the far away and long ago." He envisioned a cosmos where observation today retroactively determines the history of particles that have traveled for billions of years, a concept he called the participatory universe. This is not merely philosophy. There are tantalizing clues within life itself. The field of quantum biology investigates how living systems might harness quantum weirdness. In photosynthesis, for example, plants seem to use quantum coherence, a delicate state of superposition, to find the most efficient path for transferring solar energy. It is as if nature learned to exploit the quantum rulebook long before we ever discovered it. How far does this quantum connection go? Could the neural processes in your brain rely on quantum superpositions to generate conscious thought? The Orch-or theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests exactly that, positioning tiny structures within brain cells as the seats of quantum computation and consciousness. Yet this entire idea faces fierce criticism. The mainstream explanation for the collapse of quantum weirdness is a process called decoherence. This argues that a particle does not need a conscious observer to choose a state. It simply becomes entangled with its environment. The moment a quantum system interacts with even a single photon or air molecule, its fragile superposition is destroyed, and it behaves classically. In this view, the measurement is made by the environment long before any human mind is aware of it. So where does this leave us? If decoherence explains the data, is there any role left for consciousness to play? Or does it simply make us aware of a reality that has already been decided? The debate is far from settled. It forces a question of staggering implications. If our minds do, in some small way, shape reality at the quantum level, are we not just inhabitants of the universe but its co-creators? This intimate dance between the inner world of mind and the outer world of matter leads us directly to one of humanity's oldest and most personal philosophical struggles, the puzzle of free will itself. The feeling that you are the one making a choice right now is undeniable. Yet this profound sense of agency collides head-on with a scientific vision of a universe governed by unbreakable chains of cause and effect. Imagine a cosmic line of dominoes stretching back to the Big Bang itself. If we knew the exact position and momentum of every single domino at the beginning, could we not predict the entire cascade, including the precise moment you decided to lift your finger? This is the stark picture of determinism, a legacy of Newtonian physics where the universe was seen as a perfect, predictable clockwork machine. If every action is the inevitable result of prior physical states, where is the room for genuine, freely willed choice? Neuroscientist Sam Harris argues there is none, stating plainly that free will is an illusion. Our wills are simply not of our own making. He suggests that the thoughts and intentions that seem to author our choices simply appear in our minds, products of genetics and environment that we did not choose. This leads to an unsettling corridor of questions. Are we merely sophisticated biological machines reading a script written by our past? Some philosophers, known as compatibilists, attempt to navigate this impasse. They argue that free will is not about being free from the laws of physics, but about being free from external coercion. In this view, you have free will if you are able to act according to your own desires and motivations, even if those desires were themselves determined by prior causes. Your choices are still yours, even if the process that generated them was part of a causal chain. Science has even peered into the mechanics of a decision. In the 1980s, physiologist Benjamin Libet conducted a famous experiment where participants were asked to note the exact moment they felt the conscious urge to flex their wrist. He found that a specific brain signal, the readiness potential, began building several hundred milliseconds before the person was even aware of their own decision. It seemed the brain was initiating the action before the conscious mind had even gotten the memo. This suggests our conscious feeling of deciding might be more of a post hoc narration than the true cause of our actions. If free will is indeed a compelling story we tell ourselves after the fact, the implications for society are staggering. Our entire systems of law, morality, and personal responsibility are built upon the bedrock assumption that we are the true authors of our actions. If that foundation crumbles, how do we justify praise, blame, or punishment? The debate is far from settled, with many questioning the interpretation of such experiments. Yet the puzzle remains. If the universe is a deterministic cascade, what is the source of this powerful, undeniable feeling of choice that defines our every waking moment? This deep inquiry into the nature of causality and agency forces us to look back to the very first domino, the ultimate uncaused cause that set the entire cosmic sequence in motion, the origin of the universe itself. The ultimate uncaused cause, the first domino in the cosmic chain, was not a gentle nudge but a cataclysm of unimaginable power. From a point of infinite density and temperature, a singularity where all the known laws of physics break down, the entire universe erupted into being. This was the Big Bang, the moment space and time themselves began. For a fleeting fraction of a second, the universe was smaller than a single atom, hotter than the core of any star, and then it exploded into an expansion that continues to this day. We can trace this history back to approximately 13.8 billion years ago, to that initial hot, dense state. The evidence for this cosmic genesis is etched across the sky. Edwin Hubble's observation that distant galaxies are all racing away from us revealed an expanding universe like dots on an inflating balloon. If you run the film backward, everything contracts, converging to that single, unimaginable point. Even more compelling is the cosmic microwave background radiation, a faint, cold glow that permeates all of space. This is the afterglow of the Big Bang itself, the cooled remnant of that first explosive fireball, now just a few degrees above absolute zero. As Stephen Hawking once noted, the universe doesn't allow perfection. Its initial conditions were a specific, messy, and potent recipe. In the first fleeting moments, a period known as cosmic inflation, the universe underwent a faster-than-light expansion, smoothing it out and planting the seeds for all future structure. As it cooled, energy condensed into the first fundamental particles, quarks and electrons, which then assembled into protons and neutrons. For hundreds of thousands of years, the universe was an opaque fog of plasma, until it cooled enough for atoms to form, finally allowing light to travel freely and creating the transparent cosmos we see today. Yet the theory leaves one staggering question unanswered. What caused the Big Bang itself, and what, if anything, came before it? If time began with the Big Bang, the very phrase before the Big Bang may be as meaningless as asking what is north of the North Pole. Some theories, like the cyclic model, propose an endless sequence of universes, with big bangs followed by big crunches in an eternal cycle. Hawking's own no-boundary proposal suggests the universe has no beginning in time at all, that the concept of a starting point is a trick of our perception, much like the South Pole has no point south of it. This inquiry into our absolute beginning forces a profound shift in perspective. Why did this particular universe, with its very specific set of physical constants and laws, emerge from the chaos? The force of gravity, the mass of an electron, the strength of the nuclear forces, each of these values appears to be perfectly calibrated, set with a precision that allowed galaxies, stars, planets, and ultimately, life to form. The slightest variation in any of these numbers would have resulted in a sterile, empty cosmos. This is the mystery of cosmic fine-tuning, the uncanny sense that the universe was expecting us. This uncanny precision in the universe's fundamental settings is what scientists call the fine-tuning problem. The force of gravity, for instance, is perfectly balanced on a razor's edge. If it were just a tiny bit stronger, the universe would have collapsed back on itself in a fiery crunch long ago. If it were slightly weaker, matter would never have clumped together to form stars and galaxies, leaving the cosmos a cold, dark, and eternal void. The same delicate balance applies to the strong nuclear force, which glues atomic nuclei together. If this force were a mere 2% stronger, all the hydrogen in the early universe would have fused into helium, leaving no fuel for stars like our Sun. If it were slightly weaker, heavy elements necessary for planets and life would never have formed at all. Even the mass of an electron seems meticulously chosen. As physicist Paul Davies reflected, the universe is uncannily fit for life, as if it were expecting us. How do we explain this breathtakingly precise calibration that allowed us to exist? One profound, if unsettling, answer is the Anthropic Principle. In its simplest form, it states that we observe a universe with these specific properties because if it were any different, we would not be here to observe it. It is a cosmic version of survivor bias. We are not seeing a universe designed for life. We are simply the life that happened to emerge in a universe that permitted it. This logic leads to one of the most staggering ideas in all of science, the multiverse. If our universe is just one bubble in an infinite, bubbling foam of universes, each with its own random set of physical constants, then it is no surprise that we find ourselves in one of the rare habitable ones. In this cosmic lottery, we simply hold the winning ticket. This vast landscape of possibilities is a core feature of string theory, which suggests a near-infinite number of ways for the extra dimensions it proposes to curl up, each configuration yielding a different universe with different laws. Others see this fine-tuning as evidence of something deeper, a necessity rather than a lucky accident. Perhaps there is a single, overarching theory, a final equation that logically requires the constants of nature to have the exact values we observe. In this view, the universe could not have been any other way. For many, however, the apparent design points toward a designer, a cosmic architect who set the dials with intention. Are we the product of a cosmic lottery drawn from an infinite multiverse, or does the universe possess an inherent, life-friendly quality we have yet to fully understand? The answer to this question forces us to confront the ultimate nature of reality itself, and whether we are living in a cosmos that is profoundly alone, or merely one page in an infinite library of universes. If every possible universe exists, from one where you never clicked this video to one made entirely of strawberry jam, then our own cosmic story is just a single sentence in an infinite library. This staggering vision is the Multiverse Hypothesis, the idea that our universe is merely one bubble in a vast, frothing cosmic foam. Physicist Max Tegmark captures its scale, stating that our universe is just one of many in a grand ensemble of universes. This is not a single idea but a layered one, often described in levels. The level 1 multiverse arises from eternal inflation, the theory that the rapid expansion of the early universe never truly stopped everywhere. In this picture, new bubble universes are constantly popping into existence, each with its own separate spacetime, potentially filled with different galaxies and stars. A level 2 multiverse introduces even more radical variation, where each bubble might have entirely different fundamental forces and physical constants. In one bubble, gravity might be 10 times stronger, instantly crushing any possibility for planets, while in another, the nuclear forces are too weak to ever form an atom. This directly addresses the mystery of fine-tuning. There is no need for a cosmic architect to explain our universe's perfect settings if every possible setting is tried out in some universe somewhere. We simply inhabit the rare bubble where the numbers allowed us to be. Then there is the level 3 multiverse, which emerges directly from the quantum mechanics we explored earlier. Remember the many worlds interpretation, where every quantum decision causes reality to split. In this view, a parallel universe is born every time a particle could go left or right, every time you make a choice, creating a near-infinite tree of alternate realities. The most profound challenge this idea faces is one of science itself, falsifiability. If these other universes are permanently disconnected from our own, forever beyond the reach of any observation or experiment, can the multiverse truly be considered a scientific theory, or is it a philosophical proposition? This leads to a deeply personal question. If every tragedy is balanced by a triumph in another reality, if every path not taken is actually being walked somewhere else, does that rob our own lives of their unique meaning, or does it liberate us, knowing that in some other cosmos, every other version of us is also living out their story? This contemplation of alternate realities and the information they contain pushes us toward one of the most destructive and informative objects in the cosmos, the black hole. A star's final collapse is a surrender to gravity's ultimate victory. When a massive star exhausts its nuclear fuel, its own immense weight crushes it inward, past the point of no return. The star vanishes, leaving behind a region of space where gravity is so intense that nothing, not even light, can escape its clutches. This is a black hole, a cosmic abyss where the known laws of physics are stretched to their breaking point. For decades, we believed these objects were eternal and impenetrable, the universe's ultimate prisons. Then Stephen Hawking made a discovery that turned this idea on its head. He realized that through subtle quantum effects at the very edge of the black hole, its event horizon, particles could slowly leak out. This Hawking radiation means that black holes are not permanent. They evaporate, fading away over astronomical timescales. This revelation created one of the most profound conflicts in modern physics, the information paradox. Quantum mechanics, the rulebook for the small, states that information is never truly destroyed. If you burn a book, its information is theoretically recoverable from the smoke and ash. But general relativity, governing gravity and the large, suggests that anything crossing a black hole's event horizon is lost forever, its information irretrievably erased when the black hole itself evaporates. These two foundational pillars of physics give us two contradictory answers. Is information preserved or is it annihilated? As physicist Leonard Susskind asserted, the information that falls into a black hole is not lost, it is scrambled and returned. But how, where does it go? To resolve this, physicists have been forced to consider truly radical ideas. The holographic principle suggests that all the information describing the three-dimensional interior of a black hole is actually encoded on its two-dimensional surface, its event horizon, like a cosmic DVD storing a three-dimensional movie on a flat disk. When the black hole evaporates, this information is imprinted on the escaping Hawking radiation, preserved but in a form we cannot yet decode. This leads to another dizzying possibility, the firewall paradox. If information is to be saved, an incoming astronaut crossing the event horizon might not experience the gentle fall predicted by Einstein, but would instead be instantly incinerated by a wall of ultra-high energy particles. The paradox forces us to question our most basic assumptions about space and time. If information is truly fundamental, its stubborn refusal to be destroyed by a black hole tells us something profound about the fabric of reality. Perhaps the three-dimensional world we experience, with its stars, planets, and people, is not the most fundamental level of existence. Perhaps it is a projection, a hologram, rendered from a vast network of information stored on a distant, two-dimensional surface. A three-dimensional hologram, the kind you might see on a credit card, is not truly three-dimensional. It is an illusion, a pattern of light and interference fringes encoded onto a flat, two-dimensional piece of film. Now take that concept and expand it to a cosmic scale. The holographic principle proposes that our entire universe, with its three spatial dimensions, might be just such a magnificent projection. The information that describes every star, every planet, and every one of us could be encoded on a distant, two-dimensional surface that surrounds us. This is not science fiction, but a serious idea emerging from the deepest puzzles of black hole physics and string theory. Physicist Juan Maldaisner, whose work was pivotal here, described the holographic principle as a profound realization about the nature of gravity and quantum mechanics. It suggests that gravity and the three-dimensional space we experience emerges from a quantum system that operates on a lower dimensional boundary. This idea elegantly resolves the black hole information paradox. The information about everything that falls into a black hole is not lost inside the singularity. Instead, it is perfectly preserved, scrambled, and encoded on the black hole's two-dimensional event horizon, the surface of its point of no return. As the black hole evaporates via Hawking radiation, this information is slowly and faithfully released back into the universe. The principle implies a staggering reduction in the fundamental building blocks of reality. It suggests that the apparent complexity of our three-dimensional world is an illusion, and that the true, fundamental degrees of freedom are vastly fewer, living on a distant surface we cannot see. The most concrete realization of this is the AD/S/CFT correspondence, a mathematical duality that shows a theory of gravity in a hypothetical anti-de Sitter space is completely equivalent to a conformal field theory, a quantum theory without gravity operating on its boundary. While our universe is not precisely this type of space, the correspondence is a powerful hint that the principle might be universally true. Scientists are even looking for experimental evidence, searching for a faint holographic noise in the data from gravitational wave detectors, a subtle graininess in spacetime that would betray its projected nature. So we are left with a question that challenges the very fabric of our experience. If the universe is a hologram, are we and everything we perceive just incredibly intricate patterns of information on a vast cosmic screen? This notion that reality might be an informational construct leads us directly to the idea that the cosmos itself could be a form of immense, self-organizing computation. Our three-dimensional reality might be a grand illusion, a mere slice of something far more complex and intricate, beyond the familiar length, width, and depth we navigate every day. Theoretical physics suggests the existence of hidden realms, extra-spatial dimensions curled up into sizes so vanishingly small they evade all our senses and instruments. This is not science fiction, but a core prediction of our most ambitious attempt to unify all of physics, string theory. Imagine a garden hose seen from a great distance. It appears to be a simple one-dimensional line, but if you could shrink down to the size of an ant, you would discover a second dimension, a circular direction wrapping around the hose itself. String theory proposes that our universe is like that, but with 6 or 7 extra dimensions coiled into shapes called Calabi-Yau manifolds, fantastically complex geometric forms at every single point in space. As physicist Brian Greene explains, string theory is a framework that seeks to unify all forces and matter. Its central, beautiful idea is that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy, strings. Just as a single violin string can vibrate at different frequencies to produce every note in a symphony, a single fundamental string can vibrate in different modes. One specific resonance might correspond to an electron, another to a quark, and yet another to the particle that carries the force of gravity, the graviton. This elegant concept promises to weave together the tapestry of reality, merging the rules of the very large general relativity with the rules of the very small quantum mechanics into a single, coherent theory of everything. These extra dimensions could also solve a long-standing cosmic puzzle: why gravity is so astonishingly weak compared to the other fundamental forces. A magnet can easily lift a paperclip, defying the gravitational pull of the entire Earth. The explanation might be that while electromagnetism and the nuclear forces are confined to our three-dimensional brain, a term for a membrane within a higher dimensional space, gravity is different. It could be leaking or diluting across all the dimensions, which would explain its apparent feebleness in our world. Yet, for all its mathematical beauty and promise, string theory faces a monumental challenge: a complete lack of direct experimental evidence. The energy levels required to probe these tiny strings or uncurl the extra dimensions are far beyond the reach of any particle accelerator we could ever hope to build. This has led some critics to question whether it is even a testable scientific theory at all. But the quest continues, with physicists exploring mind-bending implications, like the possibility that our entire universe is a three-dimensional brain floating within a higher dimensional bulk, and that colossal collisions between such brains could have been the true origin of our own Big Bang. If these hidden dimensions do exist, their discovery would force a revolution in our understanding of reality, as profound as the Copernican revolution. It would mean that everything we perceive is just a fraction of a richer, deeper, and more interconnected cosmos. This relentless drive to unify all the forces of nature into one elegant equation represents the final, epic quest of modern physics. Einstein spent the final 30 years of his life chasing a single, elegant idea, a framework that could weave together all the forces of nature into one coherent tapestry. This dream of a final theory, a theory of everything, remains the holy grail of physics. The goal is breathtakingly ambitious: to unite the cosmic laws of general relativity, which govern stars and galaxies, with the bizarre rules of quantum mechanics, which dictate the behavior of atoms and particles. These two pillars of modern physics are both spectacularly successful in their own domains, yet they speak entirely different languages and become mutually incomprehensible at the extremes, like inside a black hole or at the moment of the Big Bang. As physicist Michio Kaku reflected, the theory of everything would be the ultimate triumph of human reason. It would be a single equation you could wear on a T-shirt, yet from it, the entire universe could, in principle, be derived. Primary candidates for this unified theory are as profound as they are different. String theory, as we have seen, proposes that tiny, vibrating loops of energy are the fundamental notes in the cosmic symphony. Its rival, loop quantum gravity, takes a different path, suggesting that space and time themselves are not smooth and continuous, but are woven from a fabric of discrete, finite loops, a spin network, eliminating the troublesome singularity at the heart of a black hole. The challenges are monumental. How do you reconcile gravity, which curves the stage of space-time, with the quantum actors that perform upon it? Why does gravity remain so stubbornly weak, and what is the true nature of the dark energy accelerating the cosmos? Mathematics is the essential language of this quest, but its uncanny effectiveness in describing the physical world is itself a deep mystery. Why should abstract mathematical concepts, discovered through pure reason, so perfectly model the behavior of the real world? This search for unity forces a profound question upon us. If we one day discover this ultimate theory, would it represent the end of science, answering every fundamental question about the cosmos? Or would it, like peeling an onion, simply reveal deeper, more complex layers of mystery, opening doors to realities we cannot yet even conceive? This uncanny alignment between abstract thought and physical reality is perhaps the deepest magic of science. Decades ago, physicist Eugene Wigner wrote a famous essay titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." He was struck by a profound mystery. Why should a system of logic and symbols, created entirely within the human mind, possess such a breathtaking power to predict and describe the behavior of the physical world? It feels like a miracle. Albert Einstein himself wrestled with this very question, asking, how can it be that mathematics, being after all a product of human thought, is so admirably appropriate to the objects of reality? We are not just talking about simple counting. The intricate, often bizarre equations that physicists scribble on blackboards consistently turn out to be the operating code of the cosmos. The most stunning example is the prediction of antimatter. The physicist Paul Dirac was working on an equation to describe the electron, reconciling quantum mechanics with special relativity. His math was beautiful, but it had a strange quirk. It demanded solutions with negative energy which seemed physically impossible. Rather than dismissing it as a flaw, Dirac trusted the mathematics. He proposed that these solutions corresponded to a new kind of particle, identical to the electron but with opposite charge. This was the prediction of the positron, the electron's antimatter twin, a particle that was discovered in cosmic rays just a few years later. The math literally described a fundamental part of reality before anyone had ever seen it. This power forces a fundamental philosophical divide. Are we discovering mathematics or are we inventing it? The Platonic view holds that mathematical truths exist in a perfect, abstract realm independent of human minds. A circle or the value of pi are eternal realities that we merely stumble upon and describe. The mathematician is an explorer, charting a pre-existing landscape of pure form and relation. The opposing view, formalism, argues that mathematics is a human-invented game played with symbols. It is a logical construct, a set of rules we define like the rules of chess. Its effectiveness is then a happy and perhaps inexplicable accident. So which is it? Is mathematics a human language we have painstakingly built, or is it the native tongue of the universe itself, a language we are only slowly learning to speak? If the universe is fundamentally mathematical in its structure, then this mystery begins to make a different kind of sense. The laws of physics are not just described by math, they are math. This perspective leads to a startling and modern speculation, the simulation hypothesis. If reality is at its heart a set of mathematical relations and rules, then it is not so far-fetched to consider that our universe could be running on a cosmic computer, an unfathomably powerful processor executing the code of existence. The very effectiveness of mathematics that Wigner found so unreasonable might be the most compelling clue that we are living in a constructed reality. The universe might not be the ultimate reality, but a sophisticated digital construct, a simulation running on a computer of unimaginable power. This is the simulation hypothesis, a modern philosophical argument that reframes our entire existence as something akin to an ultra-advanced video game. Philosopher Nick Bostrom formalized this mind-bending idea, proposing that if a civilization ever reaches a post-human level of technological maturity, it would likely possess the computing resources to run vast numbers of detailed simulations of its own ancestors. If such civilizations are possible, and if they have any interest in running these ancestor simulations, then the number of simulated minds would vastly outnumber the number of original biological minds. Statistically, therefore, it is far more likely that we are among the simulated beings than the original ones. Elon Musk has bluntly summarized the argument's conclusion, stating the odds that we are in base reality is 1 in billions. But is there any scientific evidence for such a fantastical claim? Proponents point to curious features of our cosmos that resemble the hallmarks of a constructed reality. The universe appears to have a fundamental resolution, a pixelated limit at the incredibly tiny Planck scale, below which the concepts of space and time lose all meaning. This is analogous to the finite pixel density on a computer screen. Furthermore, the fuzzy, probabilistic nature of quantum mechanics, where particles exist in superposition until observed, could be interpreted as a processing optimization technique. Just as a video game only renders the graphics a player is directly looking at to save computational power, our universe might only resolve definite properties when measured to reduce the processing load on the cosmic computer. Yet the hypothesis faces fierce and reasonable criticism. Many physicists argue that the pixelation at the Planck scale is a feature of our current theories, not proof of simulation. The quantum world's weirdness is just that, a fundamental property of nature, not a programming glitch. The most damning criticism is the question of regress. If our universe is a simulation, who is to say that the civilization that created it is not itself inside another simulation, leading to an infinite and arguably meaningless chain of simulated realities? The philosophical implications are staggering. If we are living in a simulation, our very sense of self, our memories, and our struggles could be nothing more than lines of code. It challenges the foundation of purpose and identity. Are our lives less meaningful if they are simulated, or does the richness of our experience, the depth of our emotions, grant its own form of reality regardless of the substrate? This leads to a deeply unsettling ethical question for our potential creators. If we are self-aware simulations, what are the moral responsibilities of the simulators? Are they obligated to minimize our suffering? If they can pause, rewind, or delete our universe, does that make them gods or merely negligent programmers? And if this is a simulation, can we ever find a way to peek behind the curtain, to see the source code of reality itself? This digital reality concept resonates powerfully with our earlier explorations, painting time and space not as fundamental, but as emergent properties generated by a deeper informational process. Space and time feel like the unwavering stage upon which the universe performs, but what if the stage itself is part of the show, emerging from a deeper, more fundamental layer of reality? The smooth, continuous fabric described by Einstein may be an illusion, a collective effect of countless tiny, discrete grains of spacetime, much like a digital photograph emerges from a vast array of individual pixels. This is the radical proposal of theories like loop quantum gravity, which suggests that space is woven from a network of finite loops, and causal set theory, which posits that reality is fundamentally a collection of discrete events with a defined order. In this granular view, the flow of time itself may not be a primary feature of the cosmos. The physicist Carlo Rovelli offers a profound perspective, suggesting that time is ignorance. It emerges from our limited perspective. Our experience of moments passing may simply be a consequence of our inability to see the complete, timeless quantum state of the universe. How then does this smooth, four-dimensional spacetime we inhabit arise from such a quantum foundation? A compelling clue comes from the strange phenomenon of quantum entanglement. When two particles become entangled, their fates are linked instantaneously, no matter the distance, a connection that seems to defy our classical notions of space. The AR equals EPR conjecture makes a breathtaking leap, proposing that what we experience as entanglement, a quantum link, might be physically underwritten by tiny wormholes or Einstein-Rosen bridges, stitching the fabric of space together. In this view, the intricate web of quantum connections between particles is literally weaving the geometry of spacetime itself. Spacetime could be a vast network of information emerging from these entangled relationships. If this is true, could we ever detect the graininess of this underlying structure? Scientists are searching for signatures of this spacetime foam by studying the light from distant quasars and pulsars. The idea is that as this high-energy light travels across billions of light-years, the tiny, frothy fluctuations in spacetime at the Planck scale would slightly jostle the photons, leaving a faint, statistical imprint on the signals we receive. Finding such evidence would fundamentally rewrite our understanding of reality. This leads to a deeply unsettling question about our own past. If spacetime is not fundamental but emergent, then the solid, unchangeable history we believe in, the linear sequence of cause and effect, might also be an emergent property. What is the true nature of a past that is not permanently etched into a fixed background, but is instead a dynamic, relational structure that arises from the present? This challenges the very bedrock of causality, forcing us to ask whether, at the most fundamental level, an effect could ever precede its cause. the classic grandfather paradox cuts to the heart of causality itself. If you journeyed into the past and prevented your own grandfather from meeting your grandmother, would you instantly vanish, erasing the very possibility of your journey? This logical knot seems to tie time travel in an impossible loop, breaking the foundational rule that cause must always precede effect. Yet, the universe's rulebook, as defined by Einstein's general relativity, is far more permissive than our intuition suggests. The equations allow for structures known as closed time-like curves, paths through the warped fabric of spacetime that loop back onto themselves, theoretically enabling a traveler to visit their own past. As physicist Kip Thorne noted, time travel is not forbidden by the laws of physics. It is the practical requirements that are staggeringly difficult. To build such a machine, you would need to manipulate gravitational fields of cosmic proportions or stabilize a wormhole, a hypothetical tunnel through spacetime with a form of matter that possesses negative energy density. But if the physics allows it, how do we resolve the paradoxes? One compelling answer is the Novikov self-consistency principle. This idea suggests that the timeline is rigid and self-correcting. Any actions you took in the past would inevitably, through a complex chain of seemingly chance events, lead to the very future you left from. You could not kill your grandfather because the laws of physics would conspire to stop you. Your gun would jam, or you would be struck by a sudden change of heart. The past is already set in stone, with your travel and your actions always having been a part of it. Another solution, popularized by many worlds' interpretations of quantum mechanics, proposes that your meddling in the past would not change your own history, but would instead spawn a new, parallel timeline, a branch universe where you never existed, while your original timeline remains untouched. This possibility forces a profound confrontation with the ideas of destiny and free will. If time travel to the past is possible, even in principle, then the future must already be fixed. Your entire life, with all its choices and chances, would be a single, unchangeable thread woven into the cosmic tapestry. The you from the future who steps out of a time machine is living proof that your path is already complete. This challenges the very core of our experience, the feeling that we are authors of our own story. Are we merely reading from a script that has already been written to its final page? These twisting corridors of cause and effect, where the future can reach back and touch the past, resonate with a phenomenon that operates outside of time entirely, the spooky connection of quantum entanglement. Einstein called it spooky action at a distance, a ghostly connection that seemed to violate the cosmic speed limit. Two particles born from the same quantum event become inextricably linked, their fates intertwined no matter how far apart they travel across the universe. This is quantum entanglement. Imagine a pair of magical coins, each spinning endlessly. The moment you catch one and see it land on heads, you instantly know with 100% certainty that its distant twin has landed on tails. They share a single, unified state, a correlation that defies any classical explanation. The particles themselves do not seem to care about the vast emptiness between them. Niels Bohr was right when he said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." For decades, this spooky connection was a philosophical debate, a seeming flaw in the theory. Then physicist John Stuart Bell devised a mathematical test, a theorem that could distinguish between a universe with hidden variables and one with true, instantaneous connection. When the experiments were finally performed, the results were unequivocal. The universe chose spookiness. Entangled particles consistently displayed correlations that could only be explained by a genuine, non-local link, a communication that appears to happen faster than light. This shatters the classical notion of locality, the bedrock principle that objects can only be influenced by their immediate surroundings. It suggests that at a fundamental level, the universe is not a collection of separate, isolated things, but a deeply interconnected web. This profound interconnectedness is not just a theoretical curiosity, it is the engine of a technological revolution. Quantum computers harness the power of superposition and entanglement to perform calculations that would take conventional computers millennia. Quantum cryptography uses the delicate state of entangled photons to create communication channels that are fundamentally unhackable, because any attempt to eavesdrop immediately disturbs the fragile quantum link and reveals the intrusion. So we are left with a staggering reflection. If two specks of matter can be instantaneously bound across 1 billion light-years, what does that say about the nature of separation itself? Are the vast gulfs between stars and galaxies merely an illusion, a surface feature of a reality that is, at its heart, an unbroken whole? This radical non-locality hints that our experience of a three-dimensional universe unfolding in time might itself be a kind of projection, a compelling but incomplete picture of a far stranger cosmos, one where past, present, and future exist together in a single, frozen structure, the block universe. The past, present, and future are not a sequence but a landscape. Every event that has ever happened or ever will happen exists simultaneously in a single, immense four-dimensional structure known as the block universe. This is the startling implication of Einstein's special relativity, a view called eternalism. Different observers moving at different speeds will fundamentally disagree on which events are happening now. Your present moment and someone else's on a distant spaceship are not the same. The physicist Hermann Minkowski, building on Einstein's work, declared, henceforth space by itself and time by itself are doomed to fade away into mere shadows. In this block model, time is simply another dimension, much like length, width, and depth. Your birth, your life, and your death are all equally real, fixed points within this cosmic loaf, just as the first page, the climax, and the final chapter all exist together within a book. This static picture of reality raises profound questions about the very nature of our existence. If the future is already written into the fabric of the cosmos, what becomes of free will? Are our choices an illusion, merely us reading lines from a script that has already been completed? And what of our memories? They would not be records of a receding past, but just our conscious awareness tracing a path through the pre-existing block, like a flashlight beam moving across a darkened map. Our powerful, undeniable feeling of a flowing present moment, of time passing, becomes a psychological artifact, a trick of perception with no basis in fundamental reality. So if the entire story of the universe is already written, what is the true nature of our journey through this frozen tapestry? This conflict between a static universe and our dynamic experience forces us to question the very essence of change itself. Heraclitus declared, "You cannot step into the same river twice, for fresh waters are ever flowing in upon you." This ancient insight captures a profound truth about our existence. Everything is in a state of relentless flux, from the swirling galaxies to the cells in your body. This constant churn of reality sets the stage for one of philosophy's oldest battles, the tension between being and becoming. Being represents the search for permanence, for the unchanging essence behind the world's appearance. Becoming is the celebration of change itself, the view that process is the only fundamental reality. The physicist sees this dance in the elegant equations of motion, which do not describe static objects but rather the dynamic relationships between them, the unfolding story of how things move and transform through time. Alfred North Whitehead championed this view with his process philosophy, arguing the process is the reality. In this vision, the universe is not a collection of static things, but a vast, interconnected web of happenings. Even the seemingly solid particles that make up your body are, according to quantum field theory, better understood as fleeting excitations, tiny vibrations in invisible, all-pervasive fields. An electron is not a tiny, permanent marble. It is more like a knot of energy in the fabric of the electron field, a temporary disturbance that has both a beginning and an end. So is change the ultimate reality, or is it an illusion masking a deeper, timeless stillness? Does the river truly change, or are we just giving a single name to an infinite series of different water molecules? If reality is fundamentally a process, a verb rather than a noun, then we are forced to ask a deeply puzzling question: what is doing the processing? This inquiry into the very nature of dynamics and transformation inevitably draws us to the most foundational mystery of all, the puzzle of why there is a universe processing anything at all, instead of absolute and eternal nothing. Why is there something rather than nothing? This question, posed by the philosopher Gottfried Wilhelm Leibniz, is perhaps the most profound of all. It cuts past the how of cosmic mechanics and asks the ultimate why. Why does a universe, any universe, exist at all? Should not the simplest, most logical state of affairs be absolute and eternal nothingness, a void without space, time, or physical law? Yet here we are, in a cosmos teeming with galaxies, life, and conscious minds. The physicist Lawrence Krauss offered a startling scientific perspective, suggesting the universe could have arisen from nothing, and nothing is unstable. He points to the quantum vacuum, which is not a true nothingness but a seething sea of potential. Here, pairs of virtual particles and antiparticles constantly pop into and out of existence, borrowing energy from the void for fleeting moments before annihilating each other. Could our entire universe be the ultimate quantum fluctuation, a single, monumental bubble of spacetime that simply refused to pop? This idea of a self-creating universe emerging spontaneously from a quantum seed is one compelling answer. It suggests that existence may be the default state, that the potential for something is woven into the fabric of nothingness itself. Others look to theological arguments, seeing the intricate fine-tuning and the very fact of existence as evidence of a necessary being, a first cause that itself is uncaused. Yet another possibility is that the universe is eternal, without a true beginning or end, cycling through endless phases of expansion and contraction. All these perspectives, however, run into a common barrier. They explain the existence of this universe by invoking a prior state, whether it is a quantum field, a god, or a previous cosmic cycle. But they cannot answer why that prior state itself exists. Why is there a quantum field capable of such fluctuations? Why is there an eternal cycle? The question always recedes one step further into an infinite regress. This is where our own consciousness re-enters the stage. The universe exists, and we are here to observe it. The Anthropic Principle reminds us that we can only ponder this question in a universe that permits our existence. If nothing were truly simpler, then why does a complex universe that can ask this question exist? Perhaps the very act of observation, of a mind perceiving the cosmos, is intrinsically linked to the fact of its being. Are we not just inhabitants of the universe, but a necessary part of its reason for existing, closing the loop between the observer and the observed in the most fundamental way possible? The universe is not just fine-tuned for life, but for observers capable of noticing that very fact. We are here contemplating the cosmos, precisely because its fundamental constants and forces fell within a razor-thin margin that allowed for our emergence. This self-referential loop is the heart of the Anthropic Principle. Physicist Brandon Carter, who coined the term, framed it with powerful logic. stating that what we can expect to observe must be restricted by the conditions necessary for our presence as observers. We could never find ourselves in a universe devoid of the ingredients for life, because such a place would have no one to do the finding. This principle comes in two forms. The weak anthropic principle is a simple statement of cosmic context. It notes that the physical parameters we measure are not random, but are necessarily constrained to values that allow for our existence. We observe a universe roughly 14 billion years old because that is the minimum time required to forge heavy elements in stellar furnaces and form planetary systems. We could not have appeared earlier. The strong anthropic principle takes a more provocative stance, suggesting that the universe must have properties that inevitably lead to the development of conscious life. It implies a kind of cosmic bias toward observers. This logic finds a powerful home in the multiverse theory. If an infinite ensemble of universes exists, each with different random physical laws, then it is no surprise that we find ourselves in one of the rare habitable ones. The anthropic principle, in this view, is the ultimate expression of observational selection bias. We are simply the lucky winners of a cosmic lottery. Its reach even extends into the quantum realm. The measurement problem, the puzzle of why a quantum superposition collapses into a definite state, is sometimes approached with an anthropic flavor. Perhaps the myriad possible outcomes of a quantum event all occur, but our conscious awareness selectively tunes into only one branch of reality, the one consistent with a stable world and our existence within it. Yet for all its explanatory power, the principle faces a sharp criticism. Detractors argue it is a tautology, a circular argument that explains nothing. Of course, we observe a universe compatible with observers, they say, but this tells us nothing about why such a universe exists in the first place. It seems to sidestep the deeper metaphysical why, using our own existence as a convenient and perhaps lazy stopping point. So does the anthropic principle genuinely resolve the mystery of fine-tuning, or does it merely reframe the question, leaving us to wonder if our own conscious observation is not just a consequence of the universe, but somehow a fundamental part of its reason for being? This intimate link between the observer and the observed draws us back to the quantum enigma, where the act of seeing seems to crystallize reality from a sea of chance. The scandal of quantum mechanics is not its strangeness, but its silence on a simple question: when does the shimmering cloud of possibilities become a single, solid fact? A particle in superposition exists in many places at once, a ghost of potentiality, until the moment we look at it. With measurement, its wave function collapses, and it snaps into one definite location. But what in this universe qualifies as a measurement? Is it a conscious mind, a photographic plate, or simply a single air molecule bumping into it? The physicist John Bell called this the measurement problem, and he labeled it a scandal for a reason. It is the unresolved heart of the quantum world. The Copenhagen interpretation, the traditional view, offers a pragmatic but deeply unsatisfying answer. It simply postulates that collapse is a fundamental, random process that happens upon observation, and we should not ask what is really happening beforehand. It draws a sharp line between the quantum realm and the classical world of our senses, but it cannot tell us where that line actually is. The many worlds interpretation sidesteps the scandal entirely by declaring that collapse never happens. Instead, every possible outcome of a quantum event is realized, but in a newly branching parallel universe. When you measure an electron, the universe splits. In one branch you see it here, in another, a different version of you sees it there. There is no single outcome, only an ever-expanding tree of all possibilities. This resolves the paradox, but at the cost of an almost unimaginable ontological extravagance. Then there are objective collapse theories, which propose a new physical law. They suggest that superpositions are inherently unstable and spontaneously collapse when they reach a certain size or complexity, ensuring that large objects like cats and chairs are always in a single, definite state. Yet another layer of explanation comes from decoherence, a powerful process that shows how a quantum system loses its coherence by interacting with its environment. The moment a particle is jostled by even a single photon, its delicate superposition becomes entangled with the vast number of particles around it, effectively erasing the quantum weirdness and making it appear classical. Decoherence explains why we do not see tables in two places at once, but it does not truly solve the measurement problem. It explains the appearance of collapse, but not the actual transition from multiple possibilities to one reality. If measurement is just interaction and decoherence is just entanglement with the environment, then the entire universe is still ultimately in a superposition of states. So why do we, who are part of that entangled universe, perceive only one specific, concrete outcome? This is the final barrier, the point where physics meets the hard wall of conscious perception. The quantum measurement problem forces us to confront the very emergence of the world we take for granted, the solid ground of macroscopic reality from a foundation of quantum ambiguity. A quantum particle can be in two places at once, yet you have never seen your coffee cup perform such a trick. The transition from that fuzzy quantum realm to the sharp, definite world of our daily lives is perhaps the most important unsolved problem in physics. We call this the quantum to classical transition, the mysterious emergence of a single, solid reality from a sea of shimmering possibilities. This is not a matter of size, but of interaction. The physicist Wojciech provided a crucial piece of the puzzle, stating plainly, decoherence is the reason we do not see quantum superpositions in everyday life. Decoherence is the process by which a fragile quantum system, like an electron in two places, inevitably bumps into its environment. It is jostled by stray photons, air molecules, and even the faint background radiation of the cosmos. With every such interaction, the system's quantum nature leaks out, becoming entangled with countless particles in the surroundings. This rapid, irreversible sharing of information destroys the delicate interference patterns that define quantum behavior. The system loses its coherence and begins to act classically. It appears to choose a single state. What emerges from this environmental filtering are specific states that are robust, states that can withstand the constant bombardment without being disrupted. Jacques called these pointer states. They are the familiar properties of our world, an object having a definite position, a specific momentum. Decoherence does not truly collapse the wave function in the way the Copenhagen interpretation suggests. Instead, it explains why we effectively perceive a collapse. It transforms the strange quantum probabilities into the ordinary classical probabilities we know from rolling dice. Think back to Schrödinger's cat. In a perfectly isolated box, the cat, the vial of poison, and the radioactive atom could, in theory, exist in a shared superposition of alive and dead. But in any real scenario, the system is instantly coupled to its environment. The air molecules in the box, the dust particles, even the box itself, all become entangled with the cat's fate. This colossal entanglement effectively records the outcome, making the superposition inaccessible to any local observer. The quantum weirdness is still there, but it is now smeared across the entire environment. We are left with a simple, classical probability. The cat is either alive or dead, and we just do not know which until we look. This forces a deeply unsettling reflection. If the solid, dependable reality of tables, chairs, and planets is merely an approximation, an emergent property born from relentless environmental interaction, how real are the objects we see and touch? Their definiteness is not a fundamental truth, but a practical consensus reached through decoherence. This concept of emergence, of complex order arising from simple underlying rules, extends far beyond quantum mechanics. It is the same principle that governs the origin of life itself, where inanimate molecules, through relentless interaction with their environment, self-organized into the first living cell, crossing the threshold from chemistry to biology. The quantum world fades into a blur of probabilities, yet the world we see is strikingly real and ordered. But how did this order, in one special corner of the cosmos, become alive? The leap from a swirling chemical soup to the first self-replicating organism is arguably the universe's greatest magic trick. This is the puzzle of abiogenesis, the origin of life from non-life. For life to begin, a collection of inert molecules had to somehow cross a vast and seemingly uncrossable chasm, transforming from a random chemical mixture into a coordinated, self-sustaining, and self-copying system. The challenge is immense. How could the exquisite complexity of a living cell, a tiny universe of molecular machines, arise spontaneously from a planet of simple compounds? Biologist Stuart Kauffman offers a profound perspective, suggesting that life is an expected, emergent property of complex chemical systems. He proposes that under the right conditions, a certain level of chemical complexity reaches a tipping point where self-organization and self-replication become not just possible, but almost inevitable. This is the emergence of order for free, a natural consequence of the universe's own dynamics. Scientists have proposed several compelling stages for this grand transition. The RNA world hypothesis suggests that before DNA and proteins, the first life was based on a molecule called ribonucleic acid, or RNA. RNA is a remarkable jack of all trades. It can store genetic information like DNA, and it can also act as an enzyme, catalyzing the very chemical reactions needed to copy itself. In this view, the first stirrings of life were not in a cell, but in a messy molecular soup where small RNA chains began to replicate, however imperfectly, kicking off the evolutionary process. Another promising cradle for life is the deep-sea hydrothermal vent. On the dark, cold ocean floor, these vents create porous, rocky chimneys that act as natural chemical reactors. They provide a constant flow of energy and a rich mixture of minerals, creating microscopic compartments that could have concentrated the building blocks of life and protected them from the harsh primordial environment. There is also the more cosmic idea of panspermia, which suggests that the seeds of life, or its fundamental precursors, are common throughout space, hitchhiking on comets and asteroids to be delivered to young planets like Earth. Yet even with these plausible pathways, the puzzle deepens when we consider thermodynamics. Life seems to defy the relentless pull of entropy, the universal slide toward disorder. A living organism is a stunning pocket of localized order, but it does not violate the second law. It pays for its order by increasing the disorder in its surroundings. A plant takes in ordered sunlight and excretes disordered heat, all while building its complex structure. Life is a master of energy transformation, a dynamic process that maintains its internal complexity by exporting entropy out into the wider universe. This introduces the role of information. At its core, a living cell is not just a bag of chemicals. It is a sophisticated information processing system, with its genetic code acting as a digital blueprint for its own construction and maintenance. The origin of life, then, is also the origin of semantic information, where molecules began to not just be, but to mean something, to carry instructions. This forces a question of cosmic significance. Is life on Earth a fantastically rare fluke, a one-in-a-trillion accident in a universe largely silent and sterile? Or is it a cosmic imperative, an emergent property so likely that the galaxy should be teeming with it? Our very existence is the only data point we have, and it stands as a profound mystery, pointing our gaze upward to the stars and the haunting question of whether we are truly alone. The silence of the cosmos is deafening. Enrico Fermi, over a casual lunch in 1950, captured this profound contradiction with a simple, devastating question. If the universe is so vast and ancient, with billions of planets that could support life, where is everybody? The sheer number of stars, each a potential sun for another Earth, suggests a galaxy that should be teeming with civilizations. The math seems to shout that we cannot possibly be alone, yet when we listen, we hear only an unnerving and perpetual quiet. This is the Fermi Paradox, the stark conflict between the high probability of extraterrestrial intelligence and the complete absence of any observable evidence for it. Science fiction author Arthur C. Clarke framed the dilemma with chilling clarity. He said, two possibilities exist: either we are alone in the universe or we are not. Both are equally terrifying. If we are the only conscious beings in this immense void, the weight of cosmic loneliness is immense. But if we are not alone, the question of who or what is out there becomes equally daunting. So what could possibly explain this great silence? One of the most sobering answers is the concept of the Great Filter. This idea suggests that the evolution of life from simple chemistry to a spacefaring civilization requires passing through a series of nearly impossible challenges. Perhaps the filter lies in our past, the leap from non-living molecules to the first self-replicating cell might be so astronomically rare that it has only happened once. Or maybe the filter is the development of complex multicellular life, a transition that took billions of years on Earth. The most unsettling possibility is that the Great Filter lies in our future. It could be that almost every technological civilization, upon reaching a certain point of advancement, inevitably destroys itself, perhaps through nuclear war, engineered plagues, or a runaway artificial intelligence. The silence would then be a galactic graveyard, a warning we have yet to heed. Other solutions are less grim but equally strange. The zoo hypothesis proposes that advanced civilizations are already aware of us, but they are deliberately avoiding contact, observing us from a distance as we would animals in a protected reserve. They might be waiting for us to reach a certain level of maturity or wisdom before making their presence known. Another possibility is that space is simply too big. The distances between stars are so immense that even a civilization with advanced technology might find interstellar travel impractical, or perhaps they communicate in ways we cannot yet perceive, using neutrino beams or gravitational waves that our current instruments are blind to. For decades, we have been actively searching for a signal. The SETI Institute, the Search for Extraterrestrial Intelligence, has been scanning the skies with radio telescopes, listening for a patterned transmission that would unmistakably be the product of a mind. So far, the airwaves have remained silent, save for a few tantalizing but unconfirmed anomalies. The implications of a confirmed discovery would be world-shaking. It would instantly answer the ancient question of whether we are alone, fundamentally altering our philosophy, our religion, and our understanding of our own place in the cosmos. It would be a humbling reminder that we are not the center of the universe, but part of a much larger community. This search forces a profound question back upon us. If we are, against all odds, truly the only conscious intelligence in the entire observable universe, what does that mean for our purpose here? Does it bestow upon us a unique cosmic responsibility to preserve and cherish this fragile spark of awareness, to ensure that the flame of consciousness does not flicker and die in the vast, indifferent dark? The answer to the Fermi Paradox is not just about finding others. It is about understanding the ultimate nature of life, intelligence, and our own solitary journey. The silence of the cosmos might not be a sign of emptiness, but a different kind of presence altogether. What if the universe is not a vast, unconscious machine, but is in some sense awake? This is the radical proposition of Panpsychism, the idea that consciousness is not a late-arriving product of complex brains, but a fundamental feature of reality, present in all matter to some degree. Even an electron, in this view, might possess a tiny spark of proto-consciousness, a raw, minimal experience. As the philosopher Galen Strawson argues, real physicalism requires panpsychism. His logic is compelling. If you truly believe the physical world is all that exists, and you accept that consciousness is real, then you must conclude that consciousness is inherently physical. It cannot magically emerge from entirely non-conscious stuff, like a rabbit pulled from an empty hat. Panpsychism avoids this impossible leap by suggesting that consciousness was here from the very beginning, woven into the fabric of space-time itself. It is not something the universe does, it is something the universe is. This perspective finds a quantitative echo in integrated information theory. This theory proposes that consciousness is not a binary on or off state, but a matter of degree measured by a value called phi. Phi represents a system's ability to integrate information in a unified, irreducible way. A human brain has a very high phi, while a simple thermostat has almost none. But if this is true, then the cosmic implications are staggering. What is the phi of a star, a vast network of fusing atoms and swirling plasma? What is the phi of a galaxy, with its billions of stars locked in a gravitational dance? If consciousness is a fundamental property, then we must ask, what is it like to be a star? Not to think like a human, but to experience a slow, burning, gravitational existence over billions of years. This is not a call for mysticism, but a recognition that the universe appears to be a vast, self-organizing system, from the formation of galaxies to the evolution of life. In this holistic view, your own mind is not a lonely exception in a dead cosmos, but a localized, intensified expression of a quality that permeates the whole. You are the universe becoming aware of itself. A galaxy does not need a blueprint to weave its spiral arms. A hurricane does not require an architect to spin its furious symmetry. These are not the products of a grand design, but of a deep and pervasive cosmic principle, self-organization. From the chaotic swirl of gas and dust, immense structures of breathtaking order can emerge, all without a central controller. The universe seems to possess an innate tendency to build complexity from simplicity, to find patterns in the noise. This is the spontaneous birth of order from chaos, a process that physicist Ilya Prigogine called the central characteristic of all evolution. He observed that the future is not given, it is built. This building happens through what he termed dissipative structures, systems that maintain their intricate internal order not in spite of chaos, but by feeding on it. They are like a whirlpool in a flowing river, a stable, organized shape that exists only because energy is constantly flowing through it. The moment the flow stops, the whirlpool vanishes. A living cell is the ultimate dissipative structure, taking in ordered energy from the sun and expelling disordered waste, all to preserve its own beautiful complexity against the universal pull of decay. This principle is intimately tied to chaos theory, where tiny, unpredictable fluctuations, the flap of a butterfly's wings, can cascade through a system to create vast and unforeseen patterns, a global hurricane. This sensitive dependence on initial conditions is not mere randomness, it is the engine of novelty. It is how a universe governed by fundamental laws can produce an endless tapestry of unexpected forms, from the branching of a tree to the turbulent flow of a mountain stream. We see this dynamic at the largest scales imaginable. The cosmic web, that vast filamentary structure of galaxies and dark matter, did not coalesce according to a preset plan. It emerged from the gravitational interplay of trillions of particles, a self-organizing system on a scale so grand it defies human comprehension. This same drive toward emergent complexity is likely what bridged the gap from chemistry to biology, where simple molecules driven by energy flows crossed a threshold and became the first self-replicating systems. So we are forced to confront a staggering possibility. Is the cosmos, on the whole, evolving toward ever greater levels of complexity and consciousness? Is the appearance of life and mind not a random accident in a dead universe, but a natural, perhaps even inevitable, expression of its deepest creative tendencies? This dynamic organization whispers of a cosmos that is not static, but is unfolding, building, and becoming. It nudges us toward the oldest and most intimate of all human questions, a question that has haunted philosophers and scientists for millennia, the question of purpose. Does this relentless climb from chaos to complexity point toward a direction, a goal, a telos written into the very laws of nature? The universe builds galaxies and minds with breathtaking intricacy, yet it never reveals its ultimate aim. Does this immense cosmic drama have a purpose, a final goal toward which everything is striving, or is it all a magnificent, aimless accident? This ancient question is the domain of teleology, the study of ends and purposes in nature. For philosophers like Aristotle, purpose was woven into the fabric of reality. He saw a telos, a final cause, in everything from an acorn becoming an oak tree to the celestial spheres moving in perfect circles. The scientific revolution largely stripped this purpose-driven view from the physical world, explaining phenomena through efficient causes, the mechanical pushes and pulls of matter and energy. Yet the question stubbornly persists, echoing in Einstein's own wonder when he said, "The most incomprehensible thing about the universe is that it is comprehensible." Why should the cosmos be intelligible to our minds at all, if not for some deep resonance between our reason and a rational, perhaps purposeful, underlying order? Modern cosmology reignites this debate through the uncanny fine-tuning of the universe's physical constants. The force of gravity, the mass of a proton, the strength of the nuclear forces, each is calibrated with a precision that allows for galaxies, stars, and life to form. To some, this points toward a cosmic architect who set the dials with intention, a universe designed for a reason. Others see only a cosmic lottery, the Anthropic Principle in a vast multiverse, where we simply find ourselves in the one rare universe that permits our existence with no deeper purpose implied. Existential nihilism takes this a step further, arguing that the universe is fundamentally indifferent, a blank canvas upon which we must paint our own meaning. If the relentless climb from chaos to consciousness is not guided by any external goal, then purpose is not something we find, but something we create. This is our profound human responsibility. We are the universe's way of generating meaning, of asking why. Our art, our science, our love, our struggles, they are not insignificant specks in a void. They are the cosmos becoming aware of itself and deciding what matters. So the question shifts from does the universe have a purpose for us, to what purpose will we choose for ourselves within it? This act of meaning-making, of projecting purpose onto a seemingly neutral cosmos, forces us to confront the very machinery of our perception and how our minds actively construct the reality we believe we are merely observing. Your brain is not a passive camera recording the world. It is an active, relentless architect building the reality you experience from a storm of raw sensory data. This is the unsettling premise of the brain in a vat thought experiment. How can you be certain that the chair you are sitting on, the screen you are watching, even your own hands, are not just an elaborate simulation fed directly into a brain floating in a vat of nutrients? Your senses provide electrical signals, nothing more, and your mind weaves those signals into the coherent world you call real. The philosopher Immanuel Kant reached a similar conclusion centuries ago without any notion of vats or computers. He argued we see things not as they are, but as we are. Our perception is not a direct window onto reality. It is a filtered, interpreted version shaped by the very structures of our mind. We experience the universe through the lens of space and time, which for Kant were not features of the external world, but the necessary framework of our own perception. Modern neuroscience powerfully confirms this. Your brain is a prediction engine constantly generating a model of the world. It uses the sparse, ambiguous data from your eyes and ears not to build reality from scratch, but to make educated guesses to correct its ongoing simulation. You do not see the light that hits your retina. You experience your brain's best guess about the source of that light. This modeling is so efficient that it often creates things that are not there. Consider the blind spot in your eye, a small area where the optic nerve connects that has no photoreceptors. You do not perceive a hole in your vision because your brain seamlessly fills in the gap with what it predicts should be there, using information from the surrounding area. This is your conscious reality, a seamless tapestry woven with both sensory threads and the brain's own imaginative filler. This leads to a school of thought known as philosophical idealism, which posits that reality is fundamentally mental. In this view, the solid, external world is a manifestation of mind or consciousness. A more modern, technological version of this is the interface theory of perception, proposed by cognitive scientist Donald Hoffman. He argues that our perceptions have not evolved to show us the truth of the world, but to hide it. Evolution favors fitness, not truth. We see a solid ground not because it is fundamentally solid, but because perceiving it that way helped our ancestors survive. A computer desktop uses icons of folders and files not because that is the true, complex reality of the computer's circuitry, but because it is a simple, useful interface that allows us to navigate it effectively. Hoffman suggests that space-time itself and all the objects within it are merely the desktop icons of our perceptual interface. They are a simplified, species-specific dashboard that allows us to take successful actions, while the true nature of the world behind the screen remains utterly foreign and unimaginable to us. So if our reality is a user interface, a practical illusion constructed for survival, what is the true nature of the world behind the icons? Is it a swirling sea of quantum potential, a vast mathematical structure, or something so alien we lack even the concepts to describe it? This profound construction of reality is not done in silence. It is a process narrated, structured, and ultimately bound by the very symbols we use to describe it, the mystery of language itself. A single word can build a world or dismantle one. From the epic tales told by ancient firesides to the elegant equations scribbled on a modern physicist's chalkboard, we have always used symbols to capture the universe and make it our own. These are not just labels, they are the very architecture of thought, shaping what we can see and what remains invisible to us. This idea crystallized in the Sapir-Whorf hypothesis, which proposes that the structure of a language influences the worldview of its speakers. A language with multiple distinct words for different types of snow enables its speakers to perceive nuances a single word would blur into a uniform whiteness. Our vocabulary carves the world into pieces, and we then mistake those pieces for the fundamental reality. The philosopher Ludwig Wittgenstein put it with devastating simplicity: "The limits of my language mean the limits of my world." If your language has no word for a concept, can that concept truly exist for you? This symbolic abstraction extends far beyond spoken words. Mathematics is a language, a system of symbols describing relationships and patterns with ruthless precision. A painting or a symphony is also a language, communicating emotional truths and perceptual realities that words fail to capture. Even our most rigorous sciences lean heavily on metaphor. We speak of the fabric of space-time, of cosmic inflation, of the flow of time. These are not literal descriptions, but symbolic bridges that allow our minds to cross into territories beyond direct experience. So this forces a profound question upon us. When we probe the mysteries of the cosmos, are we discovering a reality that exists independently, or are we, through our symbolic systems, inventing a reality that our particular minds can comprehend? The equations we write may be less a fundamental law of the universe and more a translation of that universe into a dialect our brains can parse. This intimate dance between the mind and the cosmos through the medium of symbol finds a mysterious echo in our universal response to beauty, a feeling that a certain equation, a certain natural form, or a certain piece of music is not just pleasing but true. Why should the universe be beautiful at all, and why should that beauty feel like a key to understanding its deepest secrets? A physicist will often call an equation beautiful long before they can prove it is true. There is an immediate, almost visceral appeal to a formula like Einstein's E=mc², a stunning simplicity that seems to capture an immense cosmic truth in just a handful of symbols. This is not a coincidence. For centuries, the concepts of beauty, symmetry, and elegance have served as a silent, powerful compass guiding scientific discovery. The great physicist Paul Dirac went so far as to state, "It is more important to have beauty in one's equations than to have them fit experiment." He trusted that if the mathematics was sufficiently elegant and profound, the experimental evidence would eventually catch up, a belief vindicated by his own prediction of antimatter. This aesthetic sense permeates our greatest theories. Einstein's general relativity is beautiful because it reveals gravity not as a mysterious force, but as the elegant curvature of spacetime itself, a geometric dance between matter and energy. The standard model of particle physics, for all its complexity, is built upon a foundation of deep symmetries, mathematical patterns that dictate how every fundamental particle and force must interact. But is this reliance on beauty a genuine glimpse into the universe's inherent nature? Or is it a cultural and psychological bias, a preference for patterns that feel comfortable and familiar to the human mind? We are drawn to symmetry in art and architecture, so perhaps we project that same preference onto the cosmos. The danger is clear. A beautiful theory could be completely wrong, while the true description of reality might be messy, counterintuitive, and deeply ugly to our sensibilities. Yet the track record is difficult to ignore. Time and again, from the discovery of the neutrino to the hunt for the Higgs boson, a commitment to mathematical elegance has led us to profound truths. This forces a question that resonates far beyond the chalkboard. If the universe, at its most fundamental level, operates according to laws we perceive as beautiful, what does that say about its nature? The aesthetic dimension of physics points to the most profound mystery of all, the sheer fact that the universe is not just ordered, but that its order is comprehensible and even beautiful to the minds that have evolved within it. It suggests a deep, mysterious resonance between the human mind and the cosmic code, as if we are somehow tuned to hear the universe's hidden music. Albert Einstein once expressed his profound wonder that the universe is not only lawful, but that it is comprehensible to the human mind. This is perhaps the most intimate mystery of all. Our brains evolved over millions of years to solve immediate, practical problems, to recognize predators, find food, and navigate social hierarchies. Yet this same biological instrument can peer into the heart of an atom, chart the life cycle of a star, and trace the history of the cosmos back to its first fiery moments. Why should the rules of quantum mechanics or the geometry of space-time be accessible to a primate that recently climbed down from the trees? The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics, a wonderful gift we neither deserve nor understand. How is it that abstract mathematical concepts, products of pure human reason, so perfectly mirror the operational code of the physical world? One explanation grounds this miracle in evolution itself. Perhaps our cognitive faculties, tuned by natural selection to recognize patterns in nature, accidentally became powerful enough to uncover deeper, more fundamental patterns. We see cause and effect because it helped us survive, and that same logical framework happens to apply to the motion of planets, but this feels insufficient. Does recognizing the pattern of a predator's footprints truly prepare the mind to comprehend the curvature of a black hole? Another, more ancient view is Platonic realism. This suggests that mathematical truths are not human inventions at all, but eternal, perfect forms that exist in an abstract realm. The mathematician is an explorer, discovering these pre-existing landscapes of relation and form. When we write an equation, we are not creating a tool, we are translating a universal truth into a language we can partially understand. This perspective implies a deep, pre-established harmony between the human mind and the cosmos, a resonance that feels almost like a designed fit. Could the universe itself be inherently intelligible because it springs from a rational source, a cosmic mind whose logic is reflected in our own? Yet for all our success, there are stark limits to our comprehension. The current frontier, the quest to unite general relativity with quantum mechanics, confronts us with concepts that defy all intuition and resist visualization. Our brains, evolved in a middle world of medium-sized objects moving at slow speeds, may simply lack the necessary wiring to grasp the true nature of reality at its most fundamental level. The universe may be comprehensible, but only up to a point. This final mystery weaves all our threads together, from quantum observation to cosmic fine-tuning. The fact that we can ask these questions, that the universe seems to invite our inquiry with beautiful, elegant answers, hints at a staggering possibility. The intelligence we discover in the cosmos may not be something we find, but something we participate in, a deeper unity where the mind and the universe are not separate, but are two expressions of a single, unfolding truth. Our journey ends where it began, with a sense of profound wonder. We have traveled from the ghostly pull of dark matter, through the accelerating void shaped by dark energy, and down to the quantum realm where particles dance in a haze of possibility until a conscious mind pins them into place. We have seen time's arrow as a consequence of cosmic beginnings, questioned the nature of our own free will, and peered into the abyss of black holes only to find our reality might be a holographic projection. The universe is not a fixed script performed on a static stage. It is a dynamic, unscripted, and deeply interconnected mystery, where the act of observation, the language of mathematics, and the silent compass of beauty are not just tools for understanding, but fundamental players in the cosmic drama. These enigmas are not separate puzzles. They are the very threads that bind reality together, weaving a tapestry where the inner world of mind and the outer cosmos are inextricably linked. This perspective transforms our role from passive spectators to active participants. We are not merely living in the universe, we are the universe experiencing itself, a process of self-discovery on a cosmic scale. As Carl Sagan so beautifully expressed, we are a way for the cosmos to know itself. Let this exploration be a beginning, not an end. Let it inspire you to look at the night sky with fresh eyes, to question the nature of your own reality, and to never stop seeking. The mysteries that bind existence are endless, and the greatest story ever told is the one we continue to write together, through our shared curiosity and relentless